Alright, physics fans, today is our day to review our Unit 4 material. The test is coming. Here's our disorientingly packed equation sheet. I will say we didn't quite get to everything this unit, so we are going to scratch off this part of the equation sheet. That is not something that we've talked about. All the rest of the stuff, though, we have, however briefly, discussed. So the point of this video is to try to remind you of all the big ideas and give you an example of what might be a reasonable test question for each. Okay, so our system that we spent some time reviewing earlier this unit was that of the simple harmonic oscillator. And this was described by just a point going back and forth in one dimension. And we talked about how this has some angular frequency, it has some period, and it has a regular old frequency. So the period is the amount of time it takes to go from one end to the other end and back. So going from there to there, that's one t. One period is how much time that takes. If you want to find the frequency, that's how many times it goes back and forth each second. That would be 1 over t. And if you want to find the angular frequency, that would be 2 pi times the frequency, or 2 pi over t. So of course these equations are all sort of summarized right there on your equation sheet. Now what's interesting about this expression, this is describing it as a sinusoidal oscillation. The omega inside of the cosine is what determines how quickly this math expression is changing in time. And then the x out front, this xm, this amplitude, is telling you how big the distance is from 0 to the maximum stretch. The other thing that we talked about with the simple harmonic oscillator is that the amount of energy in that system stays constant. If you stretch it out and let it go, the stretch is all energy in the spring, whereas once the block is moving, it also has kinetic energy. So this is your potential energy from the spring, and it tells you how much the spring is stretched out. That's the x. The k is the spring constant. The bigger the spring constant is in newtons per meter, the bigger the stiffer the spring is. And then you also have energy of the block, which is the kinetic energy, and that has to do with the mass of the block and the speed squared. And if you add those two together, it should be constant, and you can express that in terms of 1/2 kx squared, or 1/2 m, and I guess the v here would be the speed at any moment, but you could also write your maximum in terms of the maximum speed. Okay, so let's just start simple. Let's say we give you a problem like this, and I will give you some very simple problems that you don't want to overthink. If you says, okay, an object attached to one end of the spring makes 20 vibrations in 10 seconds. Its frequency is. So frequency is cycles per time. So the frequency here is 20 cycles over 10 seconds. 20 over 10 is 2 hertz. Okay, and I could give you a couple different versions of this, right? I could give you t, and I could ask you for frequency or angular frequency. I could give you frequency and ask for t or angular frequency, or I could give you the angular frequency and ask you for t or f. Okay, so any one of those would be fair game, and I hope that you all would do well on that. Okay, now here's another question, just trying to make sure that we understand what is this expression telling us. It says a particle moves back and forth along the x-axis from -x to +x max, so that's what this is, in a simple harmonic motion with a period t. At t equals 0, it is at xm. Okay, so I'm going to draw this out. Here's your t. At t equals 0, you're starting out at your maximum x. Then I should be able to draw out what one cycle of this looks like. I go through 0. Halfway through the cycle, I'm at my minus xm. And then I come back to 0. And then I end up back where I started at plus xm. So looking in terms of the block, that means you start out, the block is stretched out. It goes, here's your 0, here's your minus xm, here's your plus xm, and your block goes back and forth. Okay, then it says when the t equals 0.75 t, well, let's look. Here is 0.25 t, here's 0.5 t, here's 0.75 t, and then here I'm back where I started. So at 0.75 t, the block is where? It's at x equals 0, and v is, the slope of that line is positive. It's moving from minus to plus. So v is positive. And so let's look at which one of these that goes with. It is at x equals 0. That's good. You know, block out the ones that say something else. And is traveling towards plus x equals plus xm. Okay, so let's pick that one. All right, so far so good. Now, I can also give you questions involving the energy. The energy is the sum of the kinetic and potential energy for this system, and that is a constant. Now look at this. It says a 0.25 kilogram block oscillates on the end of a spring with a spring constant of 200 newtons per meter. Okay, so when you see that, you should be able to at least write down K equals 200 newtons per meter. So this is going to be the expression that helps you to solve the rest of this. If the system has an energy of 6.0 joules, so that could be kinetic or potential energy, but let's say for now it's just E. 6.0 joules. Then the amplitude of the oscillation is. Okay, now I want you to notice that I've given you a little bit of help here because the total energy is the sum of the kinetic and potential, but it also can be written as 1/2 kx max squared. Your Vmax is, I guess it would be omega times x max. So you could make a connection with the other way too. But in this particular problem, it's asking for the amplitude of the oscillation, and the amplitude in this case would be, we can find it by just a sec. Sorry, momentary brain fart. Okay, we'll use this this expression that I've bracketed right here. So E equals 1/2 kx max squared, and so here this is 6 joules equals 1/2 times 200 newtons per meter times x max squared. So this is 100. 1/2 times 200 is 100. So I could get that x max squared equals and now I'm going to divide both sides by 100. So it'd be 6 joules over 100 newtons per meter, and then I take the square root of both sides. And this question is on your review sheet, so I will let you complete this question by yourself. Now, I think, and here I'm giving you sort of a hint. I'm saying wink, 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 wink. A good free response question for the simple harmonic oscillator would be for me to give you an initial condition and for you to give me anything else about that. You could tell me the frequency of the block. I could ask you, where's the block at a certain time? I could ask you for the formula for the velocity. I could ask you for the max acceleration, etc., etc., etc. And that might be too vague, so let me at least give you a little bit of an idea of what I'm talking about. Let's say we have a problem like this, where it says a ball is hung from a vertical ideal spring where it oscillates in simple harmonic motion with an amplitude of 0.157 meters. And an angular frequency of pi radians per second. Write an expression for the displacement, the velocity, and the acceleration of the ball. So all that I would want you to do in a problem like this would be to use this expression. And I know for some of you that seems easy, for some of you that seems very hard. So let's just quickly do it. The x versus t would be this expression. So it would be x equals 0.157 meters times cosine of pi radians per second t. And then you could have a plus some phase offset, but if I haven't specified that, you don't necessarily need to worry about it. So that is your position versus time. That's saying you started out at 0.157 and at time equals 0, and then you're oscillating back and forth. Now, if you had this type of equation for one part of your, whoops, I'm getting a call. Okay, that was a wrong number. Okay, so we have the displacement. If we want to find the velocity and the acceleration of this ball, we can find that by just taking the derivative. So my velocity for the ball would just be my dx dt. And sometimes people have trouble doing this when you have numbers in here, but it's really just the same as when you had x equals xm times cosine omega t. We were able to find our v is minus, because the derivative of cosine is minus sine, so you'd have xm, and then you have your chain rule, so you have your omega that comes out, and then you have sine omega t. So sometimes I've seen that students who have no problem understanding this in the abstract have a difficult time doing it when it comes to something with numbers in it. So just notice this is going to be exactly the same. I have my xm, I have my omega. It's just that they're numbers here rather than just the abstract symbol. So this would be minus 0.157 meters, and then it would be pi over seconds times sine pi t. Okay, so this amplitude gives us something in meters per second, 0.157 times 3.14. That's the amplitude over velocity. And if we wanted our acceleration, we could just take that derivative again, and take the time derivative of this, and the time derivative of sine is just cosine, so this would be minus 0.157 meters, and then we'd get another factor of pi per second. So this would give me something with an amplitude of meters over seconds squared. That's good. Meters per second squared is the units of acceleration. Okay, so here I found my position, velocity, and acceleration. So it would be quite a fair question for me to ask you what the velocity of a ball is at time 3 seconds or something like that. It would be all right. And of course, the other important thing that we've noticed here is that this expression looks almost like x, and that the acceleration for any sinusoidal displacement is just minus omega squared times the displacement. All right, now from our standing waves, the next thing that we did was the idea of traveling waves. And traveling waves, we want to be a little bit careful because we have two different things that are going on. For the first case, you've got this string which is going up and down. Or you have, for instance, in air, you have the pressure which is increasing and decreasing. Longitudinal wave is one where the displacement is perpendicular to the direction of the wave motion, and longitudinal, like sound, is where the squish is in the same direction as the direction that the wave is moving. So we have two different speeds going on, at least two. We have the speed with which this bump is moving along the string, and we've got the speed at which the string itself is going up and down, which is connected to the amplitude. The speed of the wave, the phase velocity, that is what we call that, which is what we're talking about right here. These are the phase velocity is not strongly connected to the amplitude. In fact, in our approximation, it's not dependent at all. So this expression looks very similar, but the reason why it's different is that in addition to the omega, which again is just 2 pi over the period. The period is how long does it take the string to go from the top to the middle to the bottom to the middle to the top. So that's the same going through one whole cycle as the period. We also have another quantity called the wavelength, which is how long does it take for that wave to go to the bottom, to the middle, to the top, to the middle. So this is your wavelength, or another way to say it is from a peak to a peak, or a trough to a trough. Those are also good ways to define your wavelength. So we've got a period in time, and we've got a period in space, and those two together determine what the phase velocity of the wave is. So if you take the wavelength times the frequency, which is 1 over the period, so the speed is the wavelength over the period. All right, so one of the questions I put on your review, which is a little bit simplistic but good to emphasize. We've got a sinusoidal wave traveling towards the right. So this is a snapshot. This is not a picture of x versus t as we had with the simple harmonic oscillator. It's a picture of y versus x. So there's your y. Here's your x. This is a snapshot. We took a picture at one particular moment, and that's what the string looks like. Now it asks which letter correctly labels the amplitude of the wave. Now here's the thing that I want to emphasize. The amplitude is the distance from the 0 to the bottom, or from the 0 to the top. So d would be an amplitude. If I put something right in the middle here, this would be an amplitude. So be careful about that, because a lot of people want to have the amplitude as the peak-to-peak amplitude, but that's not the way that physicists define it usually. So this is not your amplitude, that one is your amplitude. On the other hand, if I asked you for the wavelength, a lot of people would sort of get confused because they want to go from the 0 to the 0. That is not the wavelength. The wavelength is where you go from one point in the cycle to the exact equivalent point in the cycle. So in fact, it would be going from like the 0 all the way to, not to the next 0, but to the very next 0 would be your wavelength. So that's the easier way to do it is from a peak to peak or a trough to a trough. So A would also be a wavelength. All right, now part of it is just understanding the math. So one of the questions I've given you on your review is the displacement of a string is given by y equals ym. That's your amplitude times sine of kx plus omega t. Now notice this is a little bit different from the expression here. What does this mean? Well, the fact that it's different means that this is a wave traveling in the minus x direction rather than the plus x direction. Okay, but that's not what the question is asking. It asks the wavelength of the wave. Okay, and really all this is a definitional question, because k is the thing that the wavelength depends on, not omega. Omega is how much time each wave takes. So in this case, you have k equals 2 pi over omega, or sorry, times over lambda, the wavelength. So your lambda would just be 2 pi over k. All right, let's see, do we have that? Yes. All right, and I will probably give you a pretty easy question just to make sure that you're on your toes. Sinusoidal water waves are generated in a large ripple tank. The waves travel at 20 centimeters per second, so that would be your V. And their adjacent crests are 5 centimeters apart. So if you're going from the crest to the crest, peak to peak, or the trough to the trough, crest to crest, I'm assuming that they mean like this, that is just your wavelength. So they've given us our wavelength in 5 centimeters. It says the time required for each new whole cycle to be generated is, well, you know that V equals wavelength times frequency, or V equals wavelength times 1 over the period. So if you want to find the time required for each new whole cycle, that is the period, and you can find that very easily. Okay, so our wavelength is 5 centimeters, and our speed is 20 centimeters per second. And so if I am thinking correctly with my fractions, I think that's 0.25 seconds. Yeah, so be careful. Centimeters over seconds, the seconds comes back up. All right, now this is a little bit of a tricky one. It says a transverse traveling sinusoidal wave on a string has a frequency of 100 hertz, a wavelength of 0.040 meters, and an amplitude of 2 millimeters. The maximum velocity at any point on the string is. So be careful. The thing that people think that this is, they'll see a frequency, and they'll see a wavelength, and they'll say, oh, I can just multiply these two together and get 4 meters per second. But I will caution you that that is not quite what this question is asking. It says the maximum velocity at any point on the string is. So the wave is moving at one speed. It's rippling down the string, but the various points on the string are moving up and down. So that speed has to do with the amplitude as well. So let's say that we write down our expression for the wave, right? or y equals y max times sine of k kx minus omega t. Okay, so from this I can go ahead and I can figure out what ym is because it's been given to me, so 2 millimeters. I have my sine of kx, so that would be 2 pi over the wavelength. So the wavelength is 0.040 meters times x minus omega then is going to be 100 hertz, so that would be 2 pi times 100 hertz would give me the angular frequency times t. Okay, so this is the expression for the wave, but now it's asking at any point on the string. So for instance, you could choose x equals 0, for instance. Then this expression stops looking like a wave expression in terms of x and t and just tells you about how that particular point is moving at x equals 0. So that y at point 0 would just be 2 millimeters times sine of, and then this part would just go to 0, and I would just get 200 pi hertz times t. Now, why is that important? Well, because at that particular point, if you're looking at the speed that string is going up and down, it would just be dy at 0.0 dt, which would give you your 2 millimeters times, so this had a minus in it, but we're just looking at amplitudes. So sine of minus anything, the minus would come out here, and then this would be minus 2 millimeters times, I would use my chain rule, I would get 200 pi hertz, and then cosine of 200 pi hertz times t. Okay, so then this thing is the amplitude of your velocity at that particular point, so that v naught, that amplitude, would be 2 times 10 to the minus 3, that's millimeters, 2 times 10 to the minus 3 meters, times 200 times 3.14, putting in my pi as a number, meters per second. Okay, so if I have that correctly, I think that is going to give you your 1.3 meters per second. All right, so a little bit tricky on that one. All right, now the last big idea about our waves was the idea of a standing wave. And a standing wave means that you have one wave traveling in your plus x direction, the other wave is traveling in your minus x direction. And as they travel through each other, at every point the principle of superposition tells me that the amplitudes, just the displacements that you would get from each wave, just add algebraically. You don't have to multiply them together or do anything fancy, you just add them together. And what that leads to is that you can get sometimes having what we call a node or an antinode. So the node is the place on the string where there's no movement at all, and then the antinode is where you get the maximum displacement, and that oscillates back and forth. And so the sense in which it's standing is that this oscillation is going like this, and there's a point between where that appears to be stationary. Now this can also happen in musical instruments, where instead of having a string that's vibrating, it's the air pressure that's going through higher and lower pressures. So for a pipe open at both ends, for instance, you could get a high pressure at the ends, like if you have a flute, and then a low pressure in the middle, and this can lead to a resonance in sort of the same way from the waves bouncing back and forth in that cavity. And then interestingly, you can get a similar situation, but the wavelengths in fact will be longer that you can fit in there if you have a one closed end. So this would be the amplitude of the air pressure at different points. And so drawing in these nodes and antinodes is how we were able to solve problems involving standing waves. Whoops. All right. I just got this out of order. This should have been earlier. In any case, it's a little problem involving wave description again, and it gives you the speed of the wave. And it gives you enough information that you can get the omega for this wave. So that would be 4.0 radians per second. And then it asks you to find out what the value of k is. So you can just use your v equals omega over k. So that's another one of those problems, just using the sort of the technology of this wave description a little more fluently. Okay, so sorry, this is another one of your review questions, but I'm going to skip it right now. What the heck? All right, I've got to open this up again. It looks like we had a little exorcism issue here. I'll be back with you in a minute. Okay, we're back. All right, so here's a question on standing waves. It says a string of length 100 centimeters is held fixed at both ends. So that means we've got a node at each one of the ends of that string, and vibrates in a standing wave pattern. The wavelengths of the constituent traveling waves cannot be. And then gives us a bunch of options. So let's just draw in our first couple of standing wave options. So if this is 100 centimeters in length, this is 1/2 of a full wavelength. So if 1/2 of the full wavelength for this lowest possible harmonic is equal to that full 100 centimeters, the wavelength in question would be 200 centimeters. And it turns out that's the longest wave that we could fit into this shape where we would have a node at each end. So 200 centimeters, that one's for sure okay. And I am going to just step on it a little bit and say that 400 centimeters is the answer. It cannot be that, because a 400 centimeter long wave, the shortest length that you could have for setting up the nodal pattern would be 200 centimeters. So this string is not long enough to set up a standing wave pattern with a traveling wave of 400 wavelength of 400 centimeters. Okay, now you have equations, and that can sometimes be helpful. It says an organ pipe with both ends open is 0.85 meters long. So that is the L in one of these equations. L equals 0.85 meters. Assuming that the speed of sound is 340 meters per second, and as we discussed last time, the speed is the speed at which the is the speed of the wave in the medium that the primary wave is traveling. So for instance, in a guitar, this would be the much faster speed of the propagation of a wave along a guitar string. Here it's going to be the speed of sound in air, which is somewhere around 340, maybe a little higher or lower depending on the pressure and temperature. And it asks us for the frequency of the third harmonic of this pipe. So in this case, I could just pick out that it's a pipe open at both ends. They tell us that. And then third harmonic would be n equals 3. Okay, so then I could define the frequency, just plug in some numbers. N would be 3. I'm using this equation. 3 times 340, and then that would be meters per second, divided by 2 times, and then this would be 0.85 meters. Okay, so you can plug in those and find 600 hertz. So that's not too mind-blowing. Of course, the way that I would do this problem, I'm not saying you have to do this, is I would just draw it out and say, okay, there's my first one. There's my first harmonic. My second harmonic would add 1 node. So this had 1 node. My second harmonic would have 2 nodes. And then my third harmonic would add in 1 more node. And then I can draw this in. And from this picture, I can find my wavelength, because this is a quarter plus a half plus a half plus a quarter is 1.5 wavelengths. So that would be 3 halves times the wavelength in question is equal to 0.85 meters. So you find that, then you find that your V is 340 meters per second. So this gives you your wavelength, and you've got your V, and then you can just solve it using V equals wavelength times frequency. Solve for frequency. So that's the way I would do it. But I know that some people at test time will enjoy having the crutch of these equations as well. So here's another type of question that I might give you. I showed you a lab that we did not, unfortunately, have time to complete this year, where you could measure the speed of sound by looking for resonances in a pipe where you fill it with a certain amount of water, and you can effectively make a one end open, one end closed pipe by of a particular length by moving the water up and down. So, for instance, I could give you the resonating frequency, just some number like 245 hertz or something like that, and then I could tell you, okay, the resonance was at the first resonance was at some distance, and then from that, this is 1/4 of a wave. This is 3/4 of a wave. This is 5/4 of a wave. This is 7/4 of a wave. In that case, I could ask you to use that to calculate, something like the wavelength. You can find the wavelength by taking this times 4. You can find the speed of sound by taking V equals wavelength times the frequency, which would be a number written on a tuning fork. And I could ask you to find the next resonance wavelengths by using this formula, I guess, or drawing it out and figuring it out. So this would be an okay free response question. Okay, here's one last question on tubes. It asks, what are the first two resonant frequencies that can occur in a tube of 0.5 meters long that is one end closed and one end open? Okay, so in this one, if you have one end closed and one end open, there's this. So this would be 1/4 of the possible wavelength would be 0.5 meters. So you could solve for that wavelength. And then the next one, you'd have adding one more node in. And so this would also be a node. And so, so this is 3/4 of a wavelength. It would be 0.5 meters. And then you could compare that to what are the first two resonant frequencies that it can occur in a tube. That's 0.5 meters long and has two closed ends. Okay, if you have two closed ends, then you would have a node at either end, and you could set up this wave, or you could set up that wave. So this is a little bit tricky. I would not give you this question because that's not one of our standard examples. So this one would be 1/2 wavelength equals 0.5 meters, and this would be the wavelength equals 0.5 meters. So in each one of those cases, I like drawing the picture and solving it out, but you could probably do it with the equations if you're clever. Okay. Let's see. We also talked a little bit about sound intensity. The sound intensity is in this weird decibel scale because we experience sound on approximately a log scale. Here's a little question. If the sound level is increased by 10 decibels, the intensity increases by a factor of what? Well, this is one that might be just good to remember, but if you were given this, you could figure it out. So let's compare, for instance, 10 decibels versus 20 decibels. Now, if I look at this equation, the way that it works is 10 decibels is 10 decibels times log of the intensity of the sound in watts per meter squared versus some reference intensity. So that would be my intensity of my 10. And then here, my 10 decibels times log of the intensity of 20 decibels over I10. Okay, so in this case, you can divide both sides by 10 decibels to get that 1 equals log of I10 over I0, and then 2 equals, I'm taking 20 divided by 10, equals log of the intensity from 20 decibels over I0. And then if you want to get rid of that log, you take each side, as 10 to the 1 and 10 to the log of I10 over I0. Okay, so you would get 10 to the 1 equals I10 over I0. And then you'd get here 10 to the 2 power equals I20 over I0. So you can see that this, by increasing 10 decibels, you have in fact increased your sound intensity by a factor of 10. So that's a little surprising. If you go from 10 to 20, you've increased it by a factor of 10. If you go from 20 decibels to 30 decibels, you've increased by a factor of 10 again, and so going from 10 to 30, for instance, would be increasing by a factor of 100. Okay, now our last thing that we want to talk a little bit about is our AC circuit. And we talked a lot about the RC circuit, which is just an inductor and a capacitor, and the current goes one way and it goes the other way. So you have a current that's going back and forth with some oscillation, like a cosine omega t. And the omega depends on your L and your C, the inductance in henries of the inductor and your capacitance in farads of the capacitor. And if you take that together, you get something that's in radians per second. And keep in mind, this is still 2 pi times the actual frequency that it takes for the current to go start at 0, go one way, charge the capacitor completely the other way, discharge the capacitor, and recharge the capacitor so it's at its initial condition. So this is our I versus T graph. And then in this case, the I versus T graph, the energy is sloshing back and forth between electric energy in the capacitor and magnetic energy in the conductor. And the electric energy is correlated with how much charge is on each plate of the capacitor, and then the magnetic energy is correlated with the amount of charge that we get. Now the other problem that we did in lab was we put an extra AC voltage source on the R, C, and L together. So this was your RLC circuit, and in this case we found that the same frequency where the RLC circuit oscillated was the resonance frequency of our RLC circuit. So that meant that if I tried the same voltage of the same amplitude voltage at different frequencies here, I would get some sort of a peak where I'd get my maximum current. So let's just see what are some okay questions I could ask you on this. An alternating current is set up in our LRC circuit. For which of the following circuit elements are the current and voltage in phase? Well, that is the resistor only. For the conductor, for the inductor and the capacitor, it's 90 degrees out of phase, either leading or lagging the voltage. The other thing that I think would be sort of okay to ask, definitely if you had an RLC, I would definitely think it's okay for me to ask you to predict a resonance frequency, or for me to, you know, give you the resonance frequency and L and find C, or give you the resonance frequency in C and find L, or something like that. Also, just to be aware that that is 2 pi times the frequency that you put on the function generator. So I think that is definitely a fair question. This question would be a little bit too hard, although it is exactly what we did in lab. So it says an inductor circuit operates at a frequency of 120 hertz. So if you had your angular frequency, that would be 120 times 2 pi hertz. The peak voltage is 120 volts. And the peak current through the inductor is 2 amps. And remember, in an AC circuit, this means that you're going between 120 to minus 120 to 120 to minus 120, and your current is going between 2 amps, minus 2 amps, 2 amps, minus 2 amps. It's going in between sinusoidally. And it says, what is the inductance of the inductor in the circuit? Well, you may remember that we used these equations in our lab to find the slope. So what you would do in this sort of a case, you've got these two equations that go together. You get that VL equals IL times XL, but your reactance, that capacitive reactance, is given here as, for instance, omega times L. And so if you wanted to find the inductance of the inductor, you would just solve for L. So L is going to be V over I omega. So in our numbers, that would be 120 volts from this. And these are the amplitudes that we're talking about, 2 amps. And then this one would be 120 times 2 pi hertz. Okay, so I would not give you anything harder than this, but this, at least, I think it would be okay to set up. For capacitors, the higher the frequency you go, the higher the current. For inductors, the higher the frequency you go, the lower the current. Okay, so that has been a lot in an hour of review. We've talked about simple harmonic oscillators, how they go back and forth with conserved energy. We've talked about waves, how each point on the wave acts like a simple harmonic oscillator. We've talked about standing waves, how they occur from two waves that are traveling in opposite directions. We've talked about resonances, which can happen in confined spaces that set up where the nodes must occur in our standing waves. We've talked about the RC circuit, which is essentially like the spring block system except with an inductor and a capacitor. And we talked about the RLC circuit, which you put an external voltage and which also has the resonance at the same position where you would get the oscillation frequency for the RC circuit. Okay, so good luck, happy studying, and I will see you at the test on Monday.